Here. So thanks everybody for joining and for participating in what is now, I want to say, the 5th annual Toronto Machine Learning Summit, day one. For those who are joining for the first time, welcome. It's good to have you as part of the community. We consider you part of the community when you come out to our events, and we have quite a bit to take place. So thank you so much. I hope this is just a starting point. And obviously we usually will meet in person bi-monthly, or we do this at the end of the year around this time in person. Unfortunately, we can't this year, but hopefully we can do that again soon. And I know that this Wednesday, we have a social event planned for those who are based in Toronto or able to come join us. So we've sent those details out. It's at Bloor and Spadina, and we have just a casual networking meet and greet and a comp drink that's provided, and some nice opportunities for us to meet in person, which will be after I think over a year and a half. So I'm looking forward to that. That's on Wednesday. So just a couple quick housekeeping notes before I introduce our great host and facilitator today, Sowmya. First thing is we're on the workshops today and tomorrow. You can still join. There's still space to join others if you'd like. And these are going to take place across Zoom for the first 2 days. On Wednesday and Thursday, we're on the hopin.to platform. So if you're still unsure how to join that, it's actually not open yet, but you've got the magic link, which is your own personal link to join that. We recommend getting on, testing it. If you're on a company VPN, you might have a little bit of issues. If you're on your cell phone, it's probably not going to work so well. So we recommend a desktop or a laptop. And that, again, is Wednesday and Thursday on Hopin, when we'll have the conference sessions and the kickoff and the announcement and the keynotes and so on. So that being said, thank you all for joining. I'm really, really excited to have you participate this year. Again, I know it's not ideal. It's virtual. It's some of us are like, oh my gosh, Zoom fatigue and so on and so forth. But you made it, and it means a lot for us, for all the team. We put a lot of work into this. The speakers, thank you so much for the speakers. Sowmya, who we'll have on stage in a second. They dedicate their time to give back to the community, and it's really generous of them. They're all very busy, so we're very, very grateful. And for you guys for coming out, like, it's amazing. Thank you so much again. Now, let's introduce our facilitator for this morning, Sowmya. So Sowmya is currently working as a researcher in the digital technologies at National Research Council, Canada's largest federal research and development organization. She has worked in the area of natural language processing, NLP, over a past decade in various roles, as a software developer, a researcher, educator, and a senior data scientist. She recently co-authored a book, Practical Natural Language Processing, a comprehensive guide to building real-world NLP systems, which was published by O'Reilly Media in June of 2020. And that was also translated into Chinese, possibly being translated into other languages, let's see. But her research lies in multilingual computing and the relevance of NLP beyond research, both in industry practice as well in other disciplines. So anyways, thank you so much. Sowmya, if you're here, can you join us on screen?
Yes, my video is on.
There you are. I see you. Thank you so much. Yeah, so we'll kick it off. Sowmya, if you have any participants asking questions in the chat, I always encourage them to ask questions. And as I say, the amount of helpfulness and the amount of benefit that you get from these sessions is directly proportional to the questions that you're asking, you're willing to ask. So I hope that everyone can ask questions, and Sowmya's been very generous. So I'm sure she'll be able to answer those. So thank you all so much. I won't take up any more of your time. I'll be here if anybody needs me, but I'll be in the background and I'll mute myself. Thank you so much. And Sowmya, over to you.
Thank you very much, Dave, and thank you everyone for being here today. I'm very happy to do this tutorial here. So before I get started, so the time is scheduled for 2 hours. I'm not going to talk for all 2 hours. It's probably going to be for 1.5 hours or so, and I have a 5-minute break in between, just so that we can all breathe some fresh air and come back. You can ask the questions in the chat window, and I'll keep looking at it now and then. Or at the end of the talk, we can also just have plenty of time for questions. And so I have some code examples, but this workshop itself is not interactive. So I just wanted to make that clear at the start. And yeah, let me get started. So this is what I have in mind for today's session. I'll start with a quick overview of what NLP is and talk more about how do we go about collecting and labeling data for NLP. How do we, if we don't have enough labeled data, how do we increase the labeled data set? What do we do when we just have a small amount of data set, small data set, like methods like weak supervision and transfer learning. I'll then walk through how to use these methods through a code example, and conclude the talk with some references. So that's what I have in my agenda for now. And the code and slides are in this GitHub link. I also pasted the link to the slides in the chat window. And if you go there, you'll see the same slides. I'm actually doing it from RPubs. So the slides are already online and you can go there and click the code link. So before I get started, this is about me. Like Dave also said, I work as a researcher at National Research Council Canada, and I had different kinds of experiences in industry and academia, both and also with teaching and mentoring. And I co-authored this book recently, which last year, which was published by O'Reilly Media. And about you, this is this is my expectation about you. You know something about NLP. You perhaps already faced this issue with labeled data sets, but you don't already know everything about how to address this issue. So this talk is not for NLP experts. It's more for people who got started, but who are not fully experts yet. So there's a question here in chat window. What are the username and password? I don't know what username and password those are. I mean, the links I gave are GitHub repo and RPubs, and they're all public. Okay, let me get started with an overview of NLP. So I don't know if the slide is clear enough, but that doesn't matter. I just wanted to show like everyday NLP applications we encounter, things like search engines which have a lot of NLP in them, or if you go onto the website like Amazon, you see these things like reviews that mention will be extracted. Oh, GitHub link is not public. Okay, sorry, I didn't notice that. I'll make it public during the break. Sorry, I was thinking it was public. Okay. I'll make that public in a bit. Give me a moment, like during the break. The first half does not have any code, so it's okay. And during the 5-minute break, I'll make the link public. Okay, so yeah, there are a lot of NLP applications like machine translation. You have information extraction. You have related news stories, thing that you see in various news websites and so on. And if you go to if you think about what are the common NLP use cases that people face in industry scenarios, there are text classification, named entity recognition, sentiment analysis, entity linking, many different kind of use cases. However, if you think about how are these things developed, what is a typical pipeline, NLP system development pipeline? These are the stages that you see. You start with some means of collecting data, some means of labeling data, then you get into some kind of text cleaning, pre-processing, doing some kind of feature extraction from text, using neural methods or using handcrafted features, build some models, evaluate them, keep working on improving this model, deploy these models, monitor them, and this process repeats. So if we look at this pipeline again, the very first step in this pipeline is data acquisition. However, we don't often have ready-made data sets that suit our need. So what should we do then? Why do we need data anyway? What kind of data do we really need for NLP? And how do we collect such data? So these are some of the questions that everyone starts thinking about when they start doing NLP projects and encounter this problem. So let us briefly discuss them. So why do we need data anyway? I mean, there are if you come from a traditional software engineering project kind of background, we don't start with data. So how is working on an NLP project different? So modern NLP is machine learning driven, and machine learning approaches typically require lots and lots of examples to train. to learn a task. Assuming we are engineering everything manually, we are not using machine learning at all, we still need some kind of curated data to evaluate our approach in terms of how it is doing, in terms of its accuracy or in terms of its coverage of different kinds of language that we want the software to work on. Even if we are just using some kind of off-the-shelf solution, like let's say I'm just using whatever Google Cloud provides me for, say, named entity recognition, we still need to know how good it is for our scenario. So even for that, we need some kind of label data. So good quality data sets are actually very important for building any NLP system. So when I say data, what kind of data do we really need for NLP? So different kinds of systems need different kinds of data. Sometimes all we need are large collections of documents without any additional information. Say, for example, building large pre-trained models, topic models, clustering, these kind of things. But in some cases, we need large collections of labeled data, say source and target pairs, say sentence and translated sentence, spam, non-spam emails, text classification kind of thing, question answer pairs, a sentence with some kind of named entities in it, relations between them, and so on. And typically we need, like, because we are using machine learning, these methods are data hungry. We need data that is large in quantity. We need good quality data because garbage in, garbage out. We can't take anything we can lay hands on. We need data without any ethics or privacy concerns. Not doing things like, keeping personally identifiable information, keeping racial or gender bias in training example. We don't need this sort of data. So you have to think about why is this important? What kind of problems does this kind of data pose if they get into some kind of models? We see examples of these kind of problems all the time nowadays. And apart from all these concerns, we also need to make sure that there is variety. So if we are working on legal use cases, we need data that suits that domain. Typically, if you're trying to do some kind of legal information extraction and you're using an available off-the-shelf solution from, say, I don't know, Azure or Google Cloud or something, that may not work for your scenario as well. So we need to think about all these things when we think about what kind of data do I need for a given scenario. One may wonder, okay, why do I face these no data scenarios? So here are some examples where you may not have any data to start with. There may be a very company-specific NLP problem, like say routing customer tickets automatically to different departments in your organization, for which data has to come from your company and your logs, and not, you won't have readily available data from outside. Or there is a common NLP problem, but for a very specific domain. Say sentiment analysis. It's a very common problem. Everybody is like who's starting to learn NLP, they do some kind of sentiment analysis project. But then you want to do it for financial domain. Or again, you want to build a very common NLP system, but for a new language. Like say, you want to build a named entity recognizer, but for French, or maybe even Canadian French, which may be different. Or building a very common NLP system for a new, very low resource language. Like say, we are thinking about building a machine translation system for English to OGP. So these are the kind of scenarios where you may not have a lot of data to start with, or sometimes just no data to start with. So what do we do in these kind of scenarios? One starting point, one way to think about it is, I want to collect and label my own data set. So how do we do that? Sometimes there are some labeled data sets, publicly available labeled data sets, they may suit our need. Sometimes you may want to scrape websites, like say forums, Wikipedia, news websites, and so on. So for example, Wikipedia articles have some categorizations underneath them, so you can use that information if you want. Or forums have some tags associated with them, news have some tags associated with them, and so on. So you get some kind of labeled data. Sometimes you can use social media content, or you get a lot of access. You may get a lot of access to usable internal data like logs, customer support messages, and so on. Advantages with this kind of thing is that we don't have to set up elaborate labeling mechanisms. Potentially large amount of data can be collected quickly so that we can directly jump into modeling. But potential disadvantage is we don't have means to do some kind of quality control if you're following this procedure. And also, this is not the most common scenario in real world. I'm sure some of you have already encountered this. Sometimes we end up with a new NLP problem where we don't actually have this kind of means to collect data from somewhere else, collect label data from somewhere else. So how do we obtain label data? Sometimes we collect our own data by doing surveys, user studies, crowdsourcing, and so on. So there are tools, many tools, like I have a screenshot here from a tool called Docano for annotating named entity recognition kind of data sets. Like here you have different categories: person, location, organization, event, and so on. And you just annotate them like by dragging the mouse across these entities, and then you collect annotated data like this. It keeps showing you sentences, and you keep doing this for as long as you want, as much time and resources you can provide to that, and that's how you can collect some label data. But the disadvantage is it can be very expensive, time consuming to do this kind of thing. If you want to collect the amount of data that is needed for machine learning, deep learning models. So and there are many other options like that. I just tried a tool called Label Studio to quickly create some annotated data, and I just thought I can put that here as an example. So I just took a few sentences and created a trial sentiment analyzer. That's what I called my project. And the way it works is I had a bunch of sentences, unlabeled sentences. I upload that, and then I created an annotation scheme saying it already has some schemes for different kind of NLP tasks. So I chose two categories, positive. So there are positive, negative, and neutral. In the template it provides, I chose only two categories, positive and negative. I'll get back to why I did that later. And then I just chose, this is the format of my text. Like I give a bunch of text and I want to label it as positive or negative. That's my task. And then it keeps showing me sentences from my dataset. I label it as positive or negative and submit. And at the end, I collect my dataset. Like so, the top portion is my original data, unlabeled data. And once I went through this, the bottom part is the spreadsheet I created, like the label dataset. It gives me the label that I gave here and like who annotated this at what time and what was the time taken and so on. So I found that tool to be useful. And it's just one of those tools, like it's not the best or anything. I found it easy to use for simple annotation tasks. Like if there are, if you need something to be quickly annotated and you, it's one of those freely accessible tools. So, but there are a whole lot of annotation tools like this. There is a link here which provides a listing of all these tools with comparison in terms of features, pricing, and the kind of tasks that these tools support. So that's more about how do we create our own label data. But like I said, creating our own label data is a labor-intensive process for us. Like we as humans need to spend a lot of time. And depending on the task, sentiment analysis probably does not need a lot of expertise, but some of the tasks need some domain expertise. Like say if you are working on say legal term extraction or something like that, and you want legal experts to do that kind of annotation, then that's also very, very expensive because their time is not cheap. So what do we do? Like, what do we do to collect large amounts of data sets? So one means to do that is something called data augmentation, where the goal is to increase the amount of label data that you have. But then, like how small is a small data set and how large is a large data set is actually really subjective. Sometimes just having 1,000 labeled examples is like a lot. Sometimes even 50,000 examples is not that much. Say, for example, in machine translation, you typically see over 50,000 pairs of examples for training, say English to French, or some such kind of systems for like large, well-resourced languages. For tasks like language modeling, we now have like very large pre-trained language models like GPT-3, where like no amount of data seems to be like a lot. Everything can be used. The more data, the better. That's how it looks for some tasks. So it's hard to say how small is small and how large is large. It really depends on the task, on the language, and other things like that. So the idea of data augmentation is to generate new data by slightly modifying existing label data. Some ways to do this is replace some words by synonyms or do something called back translation. I'll show what that is. Or by random insertion or deletion of words, swapping words, simulated typos or OCR errors, and so on. And there are some libraries, NLP, Python libraries that support this kind of methods like NLP aug, EDA_NLP, Snorkel, and there is also SBERT, sentence transformers, which also has some kind of data augmentation methods. So some example, like, so if there is a sentence like the quick brown fox jumps over the lazy dog, these are different ways of creating similar sentences to that, like say quick brown fox climbs over the lazy dog, or the easy brown fox climbs over the lazy dog, and so on. So these are sentences which are like which have some minor changes, which are unlikely to change the final, say if you're working on a text classification task, which are unlikely to change the final label. So you can use them as additional examples to increase the size of your training set. Another way of doing data augmentation is something called back translation. So here, this is very cool. The sentence, this is very cool, is first converted into French and then back translated into English. Then that became that's very cool. So clearly this kind of strategy is not actually useful for all sorts of NLP tasks. But for some, like say text classification, this seems to be like these kind of things seem to be like good strategies to increase the amount of label data. So data augmentation has been shown to be useful in a range of such NLP tasks like text classification, machine translation, question answering, and so on. So I personally recently used data augmentation for name entity recognition and found it to be useful there. It's commonly used in real world scenarios based on what I heard from others in the community, my colleagues who work in different companies doing NLP stuff. So in terms of resources, there is a good recent survey of data augmentation techniques for NLP, and there are a lot of code examples available online. And I'll also touch upon this briefly later when we have the code examples. But like I said, data augmentation works in very specific scenarios, and sometimes we may not even have those kind of scenarios where it works, and we may end up just having small data sets. So what do we do in such scenarios? So there are different ways of addressing how to the scenario of what to do to get more label training data. This is from, so this categorization is from Stanford, a blog from a couple of years ago, I think 3 or 4 years ago. The first way obviously is to go to traditional supervision, where you ask some experts to do some hand labeling of more training data, to create more training data. But as we spoke about that before, it's expensive. There is something called active learning, where we estimate what data points are more valuable to solicit labels for. Then we send them to an expert, and then we label only those and leave the other ones. There is something called semi-supervised learning, where you use some kind of assumptions to automatically label unlabeled data. Like say one easy thing could be like if look at the prediction probabilities or prediction confidence or something like that, and highly confident examples can be added to your label set and then retrain. Or there is something called weak supervision, where the idea is to create some noisy labels efficiently, like automatically, and then from there build some model and then go from there. Or more recently, a more common approach is to do transfer learning, that is use pre-trained models trained on some other tasks, and use it on a different task. So I'll talk more about weak supervision and transfer learning in this talk. And I'll just give a very brief overview of the others. So before I go there, I see that there is like one question. Okay, so what does swapping words mean in data augmentation? So this is what I mentioned, that data augmentation does not suit all scenarios. In some kind of text classification scenarios, they just create more data by changing the order of the words. And that also works in like some NLP scenarios don't care more about word order or syntax. They deal more at the level of the lexicon itself, like words themselves. So in those tasks, changing of the word order may not matter that much. And those are the scenarios where it suits more. And usually when people do this kind of data augmentation, they don't look that much into the quality of the examples generated, because the goal is to create more data to train the models. And people have shown in the past that this approach works. So this won't create you quality data, because you're still not doing anything to like manually inspect the data or something like that. So it has been shown to be beneficial in some tasks. That does not mean it works all the time. So yeah, that's what I can say about that. And we'll talk more about how and why this kind of noisy labeling kind of approaches still work for NLP. And this is also in scenarios where you really don't know how to create more label data. Like an ideal scenario is just that you spend your time and effort using expert annotations and doing traditional supervision. But data augmentation or weak supervision, these are all solutions in scenarios where you actually don't have that good quality training data. Like you have a small amount of good quality training data, but not large enough to use deep learning or machine learning or any such models. So that's the scenario where you use data augmentation. Okay, so let me talk briefly about weak supervision. So like I said, generally most learning methods used in NLP are data hungry. However, it's time consuming and expensive to hand label so much data for each and every new problem. And it's also that sometimes we may have to update our existing labels to suit changed guidelines. Like we may start with some kind of labeling scheme, build some data set, build some model, but for a period of time, we may want to change that scheme. Or we may want to just update our data set. We don't want to keep the same training set like forever. We want to change with time. It's not so uncommon in real world. It's if you're working on a research project, it may sound strange, but if you're actually working on something that's deployed in production, then it's not uncommon to see these scenarios where you need to update your labels, or you need to create a new training set and retrain on the new updated set instead of the older one. So how do we handle the costs or time taken to repeat this process of data creation each and every time? Weak supervision provides one option, one solution for that. It refers to this kind of approach where you rely on imprecise training data, noisy training data, which is not perfect, which may not be of super high quality, and which is also potentially generated automatically. So here's an example of how it may work. So here, this example is for a scenario like, say, you want to create named entity recognition data set. So you start with some kind of unlabeled documents from whatever domain, like let us say legal domain. And then you write some kind of labeling functions, like say using some lists of names or using some rules, heuristics, like if something is starting with a capital letter and it's a proper noun, then maybe it's a name, some such rules. And then you write a lot of such rules and you try to label your data using those rules. And you build a model to somehow aggregate these rules and create one label data to train final NLP model on these aggregated labels. So this screenshot is taken from this library called skweak. You can take a look at that. That provides some functions to implement this kind of weak supervision. And I'll also show an example later in a bit. So here's another example of weak supervision from Snorkel, who also seems to be one of the sponsors for PMLS this year. Here, it's the same thing again, like you start with some unlabeled data and you write a collection of noisy labeling functions. Like say, if I'm taking the problem of say spam and not spam, and then I want to say anything that has all caps is a spam, or anything that has a URL is a spam, or something like that. These are some of the labeling functions I can write. The labeling functions are primarily some kind of rules. based on, say, regular expressions or lists of words or things like that. And then at that point, you need some kind of label model which aggregates these labeling functions, because for the same instance, different labeling functions can give different output. So we need some way of aggregating those labels. And this is how, at that point, once you aggregate all the labels from different labeling functions, you have some training data set, which was created automatically, which is not of good quality, but it is still a training data set which has some labels. And you use those labels to build a model. So when you listen to me describing like this, like we start with no hand label training data, we write this set of rules, and then we create a noisy training data set. The first question that may occur to you is, what's all this? Will it really work? So when I first heard about this, that was my question as well, a few years ago. And so how does it work? Like, I mean, even if I say like, I use these unlabeled data sets and then write these label functions, or I can use data augmentation like I mentioned before. There is also a third way that Snorkel does it, which slices the data set, specifying where the model has to be more stronger, which are more difficult examples and so on. So how does all these things work? How do we write these labeling functions? Like I said, some examples are using regular expressions, lists of words or phrases, patterns, like say, like I mentioned earlier, if it's a proper noun, and which has a capital letter, starting with a capital letter, proper noun, these kind of things. Such labeling functions should basically realistically cover several examples in your unlabeled data sets, and there should not be too much of overlap between them. And they should have like high precision and good coverage. I'll talk more about these things when I talk about the actual code example. So if these things seem a little bit confusing to you right now, it's okay. I just wanted to give a more conceptual overview before talking about a specific use case. There's a tool called Data QA, which also does this kind of stuff. And they have a lot of examples of how do you write such rules for different use cases, like say for classification, for name entity recognition, and so on. You can take a look at that later. Such rules are basically useful to create this kind of noisy label data. And we can also use this kind of label rules to, when the data set is imbalanced, when you have a labeled data set, but it is imbalanced, to increase the labeled examples of rare class. Again, in these scenarios where if your data changes or labeling guidelines change, you can still use some of these previous rules without having to start from scratch. And this kind of system is probably easily explainable. So it works with if it works with a decent precision, then maybe it can be a strong baseline also for your future machine learning and deep learning models. However, all these things sounds good. Does it really work? This was the question I had, and I'm assuming at least some of you may have. Like when I talk about these noisy labels and you don't, you create label data automatically, will it really work? So apparently Snorkel is deployed in real world in many major institutions across industry and government and research. Companies like Google, Microsoft, FDA, DARPA, a lot of people are using Snorkel for doing this kind of weak supervision based modeling. And it's also if you go to the Snorkel website, you see a lot of examples of how, say, IBM is using a Snorkel and conversational agents, or how Apple is using it, or Google, Intel, all these companies. So although this whole idea of starting with low quality data set it sounds somewhat, shady, and you may get skeptical, it actually may work with some constraints. You still need to know a lot about the domain itself. So I'll talk more about how to use, say, Snorkel to build one such kind of data set in some time. So I talked more about weak supervision, but before this, I also mentioned active learning. So I'm not going to do anything with active learning in this tutorial, but I just wanted to put it out there so that you can take a look at that later. And there's also a talk in TMLS on human in the loop machine learning by Rob Monroe, I think on Thursday or Friday. You can Wednesday or Thursday, you can take a look at that. So the way active learning works is I start with some unlabeled data, but then I have some specifications on which of these need to be labeled by a human, which of these need not be labeled by a human. So then based on that, I send some data to the human, and they label the expert, like human expert, then they label the data. So this cycle goes on. I build a classifier with some amount of label data and then decide on what to send to human, and then add that back to my training data and retrain the model and so on. So that's how active learning works. And this is also a common methodology used to in these data scarce scenarios. I also talked about semi-supervised learning. And this is more like active learning without a human. So what you do is you start with a small amount of labeled data set, you build a small model, and then based on, like, say, some kind of, so you build some pseudo labeled data set with that model, but then you have some means. When I used semi-supervised learning a few years back, what we did was we used the confidence, the probability that the model gives with each prediction, and anything that is above a threshold, we just added it back into the training set so that we create a larger training set, and we repeated this process periodically. So that's how semi-supervised learning can be implemented. That is, you don't have a human in between who keeps annotating text. You use the predictions of the model itself to decide which of this data is good enough to be added as training data, so that we can retrain the model and deploy it later. The advantage of semi-supervised learning is just that it may save you some time and money, but then the disadvantage is that because there is no human intervention, there's no guarantee about data quality. However, even this is commonly used, and it's also known to work in certain scenarios. And the final method I want to talk about, introduce, is transfer learning, which some of you may be familiar with by now because it's been very popular in the past few years, where you take a pre-trained model which is trained on a different task and tune it to your own target task. Like, say you take a model trained on, say, machine translation or language generation or those kind of things, but then you can tune it to, say, text classification, name native recognition, those kind of things. So that's the idea of transfer learning. In a real world scenario, you may use a combination of all these methods. So this is an example I took from this book called Human in the Loop Machine Learning by Robert Monroe, who is the person giving a talk at TMLS this year. Let us say you have a large pool of unlabeled data. You can use active learning, ask the human to label some items, you create some small amount of training data with those labeled items. You build a model, you deploy it, but you still have a lot of unlabeled examples. So at that point, or you can use transfer learning. You can use the existing model to start or augment some training. You build a model, you deploy it on unlabeled data, and you can again do active learning, and the process goes on. So you can follow, it's not that if you follow semi-supervised learning, you have to stick to that, or if you follow transfer learning, you have to stick to that. You can use a combination of all these things in a real world scenario. So I gave you an idea of a lot of different kind of methods. I'll try to summarize it here a little bit and then take a short break, and also make the GitHub repo public in the meanwhile. And we can have some time for questions as well. So we spoke about a bunch of methods here. So what do we do? What is the way forward when we don't have any data to start? First of all, we need to understand our requirements and create a small amount of labeled, manually inspected, high quality data set. Say, for example, using Label Studio like tools. I think this part is not discussed that much when we listen to NLP tutorials or look at the textbooks, but I think that part is non-negotiable. We need to have some small amount of labeled data set, at least to evaluate other approaches that we take. If there is an off-the-shelf solution, like a cloud service provider, like, say, Google Cloud, Azure, AWS, they all have some kind of NLP services. If there is a service that suits your requirement, then you can always look at it, evaluate that solution. And for that, you can use this high quality labeled data set that you created to see how that provider performs for your data. You can create automatically labeled data and build a model using weak supervision. Again, evaluate that model with your high quality test data. And at that point, you manage to get some label data through automatic labeling or by other means. You have slightly larger amount of data set. There is this question here from Ken on synthetic data offerings. I don't know about AI.delivery. I don't know about the approach that they follow. If they provide data, synthetic data that suit your problem scenario, you can try that out, but it still does not take away the fact that you need some kind of labeled data set, like high quality manually labeled data set to evaluate how this approach works for your own scenario. I don't know if that answers your question. So like if we look at the previous slide, I said if you don't have a data set, you start with some small amount of hand labeled data. You can evaluate an off-the-shelf solution. You can look at weak supervision. So you manage to build some label data. You manage to build some weakly supervised models. So at that point, you have some baseline. What do you do from there? You can evaluate transfer learning if a similar model is available. Sometimes even that is not the case. Consider semi-supervised learning or active learning, whether if it will be useful. And slowly, so I'm just trying to, like in this 2 slides, I'm just trying to show some pipeline of how do you solve this task when you're starting from a no data scenario, building a small data set, building a strong baseline with weak supervision, exploring like these other things like transfer learning, semi-supervised learning, active learning, things like that. Over a period of time, once you build a larger data set, then you can explore more supervised machine learning or deep learning models. So usually, like in a practical scenario, this is what you would do when you see a new NLP problem. You don't have an NLP labeled data set. So I mean, it may sound fancy to use deep learning currently, but this is what usually happens. That's what I'm trying to tell. So I'll stop here for a few minutes. We can discuss some questions, and I'll also make the GitHub repo public in the meanwhile. I'll stop the screen share for a bit. So yeah, we can have like, I don't know, some 5 minutes for questions and then I'll resume. So yeah, in the meanwhile, I'm going to make the GitHub repo public. So we can, I mean, you can start, I don't know, asking or typing in the chat window. Okay, the repository should be public now. And okay, so is the focus always towards supervised learning with all these methods? Yes, with the methods I'm discussing, the focus is towards supervised learning because not all NLP tasks are suitable for unsupervised learning. Like say, you have these tasks like machine translation, name entity recognition. The most common way of solving these problems as of now is still supervised learning. And the second question is, has weak supervision been applied successfully outside of NLP? Actually, if you go to the Snorkel website and look at the case studies, my impression is that it's more successful outside of NLP. Like there are examples of it being successfully used with radiology, X-rays, and things like that. So, so I think it's more successful outside of NLP than with NLP. And methods like data augmentation, for example, although I don't stress a lot on that, data augmentation has actually been very successful also in vision, not just NLP. So we have one more question from Krishna here. I often get confused with the terms fine-tuning, transfer learning, and zero-shot learning. Can you explain the differences between them? So fine-tuning is a part of transfer learning, I would say. Like when you're doing transfer learning, typically you have a small amount of training data for your task, but you have a large pre-trained model from somewhere else. So what you do is you use this training data and tune the parameters of the larger model so that it's suitable for your task now. Like let us say you have this model, like say, I don't know, BERT, and you want to do sentiment classification with it. So you take some amount of data labeled with sentiment and then use that to tell the model to adapt to this scenario, to the sentiment classification scenario. So at that point, you still have some training data, some test data, and a large pre-trained model if you're trying to do transfer learning and fine-tuning. However, when you talk about zero-shot learning, you typically don't have any training data. You still have some test data. Like say you want to directly see without any fine-tuning, without any training, what is going to happen? Can this large model like say GPT-3 or BERT so zero shot is basically like 0 examples. Does that make the distinction clear? Like, let us say if I have a model trained on English sentiment analysis, but I'm directly using it on doing French sentiment analysis without doing anything. That is a case of zero shot, cross-lingual zero shot usage. Or if I have a named entity recognition model trained on, say, I don't know, news documents, but it somehow works also on legal documents without doing anything. So that's an example of zero shot. It's not like, okay, this is an interesting question. Like, is there really learning in zero shot learning? It's more like zero shot transfer. There's not like, it need not necessarily be some kind of learning, but it can be something like this model already learned something that is more generalizable. So it's more like, you can call it zero shot transfer instead of zero shot learning. Okay. Can I do sentiment analysis on data with no historical info, like using an unsupervised algo? This is a question from Srikant. So for sentiment analysis, that is possible because it's a kind of problem where you can get far with rule-based work, like say using a collection of positive versus negative words, or using some rules saying if they are looking at number of positive adjectives versus negative adjectives, these kind of things. So there are existing sentiment analyzers that don't rely on any machine learning. So for sentiment analysis, it is possible, but it need not be possible for all NLP problems. Okay, there is one more question. In areas where domain knowledge is lacking, how does one effectively apply weak supervision? So this is the problem with weak supervision. You really need some sort of domain knowledge. It's because weak supervision relies on these labeling functions, some kind of heuristics, and to write those heuristics, you need the domain knowledge. So, I mean, the only solution to apply weak supervision in scenarios where you also don't have label data is to get some kind of domain knowledge, hire a domain expert. Because even in this transfer learning, in this example, some snorkel with radiology and stuff, there were some people, radiologists, who were helping the people who developed these solutions with writing these heuristics. So I think that part is non-negotiable there with low data scenarios. Okay, I look at this one more question probably and then get to this case study part. It doesn't take a lot of time, so we'll still have a lot of questions time for questions at the end. So how useful would it be to use k-means clustering for text data sets that do not have labels? I think it really also depends on your scenario. I've seen clustering being used as a first stage before you apply any other machine learning methods. Like say, for example, there was some work some time back from ETS, Educational Testing Service, I think, and also Microsoft on short answer grading. That is like some kind of question answering scenario, but more in an educational context, exam test taking context. Where one approach followed was, the paper is called Power Grading or something. It's from Microsoft, where they followed this approach. They first used clustering to group similar answers together, and then graded the most representative answer from that similar answers using some machine learning or deep learning model, and then used the same grade for all things in the cluster. So I can say, I mean, it really depends on the scenario. Clustering is useful in scenarios where where the data does not have labels, but it also depends on the scenario. Like say, for example, your problem is named entity recognition, then maybe clustering is not very useful there if you don't have any label data. But it could be potentially useful if you're working on, say, some kind of text classification, but if you want to, like, the categories are more like news categorization or something like that. Like you have documents that talk about news, that talk about politics and so on, but you don't have label data. In those kind of scenarios, clustering may be more useful. Okay, there is a question on how to evaluate the quality of the data set created in this semi-supervised learning use case. So usually what we do is we don't go through that stage of quality evaluation because we are not using the data to test. We are still, our test data will still be the label data set. We are using this pseudo label data set to add to the training data. So as far as I know, in my experience, there is no quality assessment for that kind of data set. It's the same even for this data set created with weak supervision or with weak supervision. So you don't do quality evaluation for doing the training data set created automatically, but you use the same high quality test set to evaluate these models. Do you think the pre-trained Google NLP models could work well on some noisy IT? Okay. In my experience, BERT transfers pretty well to a wide range of scenarios, not everything. But there are also other models. So for example, I was recently involved in a industry project where the data comes from seaports, a lot of textual data from seaports where BERT itself did not do well. But then there are other models like BERT-like models, like say sentence transformers as BERT. Those things did slightly better for that scenario. So I would say there is no universal model that works on all scenarios, but generally these pre-trained models, the new large pre-trained models like BERT, have been doing well in a wide range of scenarios, if not everything. So it doesn't hurt to try with that. That's what I want to say as an answer for your question. Okay, maybe I'll stop the questions here and we'll resume them later after I finish this part. And I hope the GitHub repo is now accessible for everybody. I mean, you don't need that repo right now during this talk because I'm just showing screenshots of some code here, but not discussing it in detail. You may need it later if you want to go through the examples. Okay, so before I proceed, there is one more question here. I'll just answer that. So how do we know if the pseudo label data set is benefiting or having the training? The only way to know is to see how it is performing on the test data. If the model is performing poorly than before, then that means that this pseudo labeling is not working. Something else needs to happen. Okay, I'll stop looking at this chat window because questions keep coming. So I'll get back to that later. So I'm taking this very common problem of sentiment classification of sentences into positive and negative. And I'm going to show how we can apply some of these methods that I just discussed to this scenario. And there is a label data set that I'm going to use, but I will use as if part of it is unlabeled and see how I perform. There's a reason why I chose such a common problem and a commonly existing data set. It is common. It is a well-known problem, so we have many ready-made solutions available. So we can easily compare it with how my automatic labeling works with existing, if we compare with existing solutions. It's a common problem, but the dataset I chose makes it slightly difficult to use off-the-shelf solutions. Because I have only positive and negative in my dataset, I don't have neutral. But most of the off-the-shelf solutions also have a prediction called neutral. So the reason why I'm creating this problem is to just kind of scenario where you don't have your problem does not exactly fit what is available out there or solutions available out there, and you need to do something else to customize. So I just wanted to create that scenario to discuss some of these things I conceptually talked about before. So this is the data set I used. It's a very commonly used sentiment analysis data set. It has a couple of sentences. Each one has one of the two labels, positive and negative. Sentences came from 3 websites, Amazon, IMDb, and Yelp. And there are like 500 sentences per category per website. So I used the Amazon part as my labeled test data everywhere in the code examples. And the IMDb plus Yelp part, I take the labels sometimes, like when I train a traditional supervised model, but I also use it as if it's unlabeled data when I do weak supervision. in real world, you may have to create this kind of labeled examples like this final part here. In real world, you may have to create that part using some tools like Label Studio or Docano, or if you're lucky, you have some kind of internal label data there. So here are the methods I'm going to try with this data scenario. So in the no label data scenario, where I just have labeled test data and I'm going to use the training data as if it is unlabeled, I'm going to try 3 options. Use a cloud service provider's sentiment analyzer, just not do anything, just use my test data and compare my test labels with predictions from the provider to see how it is doing. Use an off-the-shelf free public library, and use weak supervision, where I take my unlabeled training data, labeled test data, I create a noisy label training data, and then build a model. And I compare this scenario, this no label data scenario, also with a label data scenario where I have everything labeled, so I can train my own sentiment classifier from scratch, or I can try transfer learning where I use an existing pre-trained language model and tune it to my task. So I'm going to try all these methods and see for this commonly used sentiment classification problem, which I twisted a little bit by removing the neutral category. How am I going to do in terms of the methods that we just discussed? So for my data set, I mean, I need some way of representing this text. So I'm using 2 methods to do feature representation. First of them is just bag of words. And I'm not going to talk about what is bag of words because I'm assuming most of you are familiar with that because I'm assuming at least some of you have used NLP before. And I'm trying another representation from sentence transformers. And the reason I chose these is to illustrate one very simple text representation and one state-of-the-art representation as means of feature extraction from text. Okay, so let me start with the scenario of no data. So when I'm saying no data, I'm still saying I have some small labeled test data. I'm not talking about where we don't even have a test data, because if we don't even have a test data, we have to create that first. There is no way to evaluate anything if we don't have that test data. And that test data should be properly hand labeled with like a high quality test data. Okay, so when I'm saying no data, so I have labeled test data. I don't have any training data. Let us say I just don't have anything. I don't even have unlabeled training data. What should I do? So I tried sentiment analysis that is provided by Azure Text Analytics. The source code is here in this URL, but so how to use the service is also provided in that URL. My code is taken from that example there. There are 2 keys that it provides. There's an API key and there is something else. I took them off from my public GitHub repo, but you can use a trial version, get those things and try it on your own. The trial version also comes with some free queries per month, and that should be enough to just test it out for now. And in a real world scenario, your company probably has money to subscribe to these things. So what the sentiment analysis from Azure Text Analytics does is it applies their sentiment model and gives some label with some confidence score. It has 4 labels: positive, negative, mixed, and neutral.
Oh my God.
What happened?
See these guys hugging?
Okay, I don't know, it's somebody's audio. Okay, so yeah, this is what Azure Text Analytics does. If I want to apply this to my scenario, here are a few things to think about. So my data set has only positive and negative labels, but Azure Text Analytics is providing me 4 labels: positive, negative, mixed, and neutral. So what should I do about this mixed and neutral? I'm talking about like a hypothetical problem scenario, sentiment analysis problem scenario, where I just have to do positive versus negative. I don't want any other category. But the off-the-shelf provider is giving me more categories. So what should I do? The second thing you need to think about when you're evaluating an off-the-shelf provider is this a permanent solution? Or should you start thinking about collecting label data by other means eventually? Okay, so this is a very simple piece of code to do sentiment analysis with Azure Text Analytics. Like I said, we need to get a key, API key, and it generates an endpoint for us. We need to query that endpoint and get some labels for sentences. What I'm doing here is basically I'm taking positive and negative, and for neutral and mixed, I'm just giving a new label which does not exist in my data set, and I'm discarding those things when I'm just seeing what happens. So with this kind of with using Azure Text Analytics, if I build a confusion matrix on my test data set, I get like 84% accuracy on the test data set, which is not actually bad. Like we have to keep in mind here that I just have my labeled test data. I did not build any model. I don't have any training data. I just used Azure Text Analytics, and I already got 84%. So that's pretty good. But the problem here is like at least 10% of my test data is labeled by Azure Text Analytics as mixed or neutral. But according to my labels, it's not mixed or neutral, it's positive or negative. So what should I do with those, with that kind of scenario? So this is something you need to keep in mind if you are working with an off-the-shelf solution. Like your categorization, your labels should match exactly the labels in the off-the-shelf solution. If they match, that's good. But if they don't match, what are you supposed to do? So like I said, I'm saying this again and again. I just wanted to create some scenario which is more closer to your real life scenario, where you may find an off-the-shelf solution, but it does not exactly match your scenario. So these are the kind of things I want to introduce to just make you think about how do you, different kind of possible things that may happen to you. So in this case, say for example, I have my data set which has positive and negative, only 2 categories. I decided to use Azure, which has more than 2 categories. I still got 84% accuracy on my test data set. But then I have 10% of my test data set, which is basically useless for me because they don't match my categorization. So that's the kind of situation you have with the solution. The second option I looked at is a tool called TextBlock. It's a Python library which has a sentiment analyzer. So here also, I think it has positive, negative, and neutral. And here, many more of my test data set is, many more examples in my test data are tagged as neutral by TextBlock. And the performance here is far less, like my accuracy is only 62% here compared to Azure. So clearly, I can discard this solution in this scenario. Like TextBlock is performing far worse than Azure. And also it still does not have the solution for this, my positive versus negative problem, where there is a neutral category. However, it's free. So if you don't have any other option, and if you don't also have like money for using the services of Azure, maybe it's not a bad point to start with. Like 62% when you don't have any data, it's not that bad. And then from there, you have to think about what to do. How should you increase the performance? How do you build a training data and so on? And even here, you can follow the semi-supervised technique because Azure also gives some confidence associated with its decisions. So you can still follow semi-supervised techniques and see like if the confidence is high, you can start creating a noisy training data from Azure predictions and then stop using Azure at some point and build your own model. That's also possible. But these are the scenarios, these are the 2 scenarios where you don't have any training data. You looked at an freely available solution and you looked at Azure. And we are comparing them in terms of classification accuracy. We see that Azure is doing like pretty well without any training data. We have 84% accuracy. But so the positive thing is you don't have to worry about setting the stuff of up building and maintaining a sentiment analyzer and so on. You can quickly get an MVP and running. However, like I said again and again, it only works if you have a problem that exactly matches the specifications of an available API. There's no possibility of customization or modification. We don't know what the model is doing. And depending on how much you use, if you have to query Azure several thousands of times a day, obviously it will be very expensive. So will this be a long-term solution for your problem? So these are all the things you need to think about in this absolute no data scenarios where you just have a small labeled test set. And also, like there is also one other thing to keep in mind. In this case, in my experience, I've seen two scenarios. In my experience, the existing solutions like Azure or Google, they don't do that well for very specific domains, like say legal domain. So I worked in legal software company for some time, so that's something I'm most familiar with. So they don't do that well with legal domain. So even as a first solution, they may not be that good. And the second thing I have seen is this semi-supervised approach that I just mentioned, like use Azure or something or some such provider initially to create some kind of pseudo label data for you, and then use that for training depending on the confidence estimates. So there's a question from Ken here. Is there a recommended label data set for legal data set size for weak supervision? I don't know of any such recommendation. I think there is no clear recommendation on how big should your data set be for weak supervision. I think it just depends on your scenario and the amount of data that is actually available to you in the first place. The more, the better too. Okay, so this is the no data NLP situation. Like I just have a labeled test set. I don't have any training data, so I decided to rely on off-the-shelf solutions. That is the scenario, and this is what we learned for this problem. For this problem, even in that scenario where I don't have any label data, I managed to get 80% accuracy, but it has its problems. The second scenario I'm going to talk about is weak supervision with Snorkel. Here, I'm using my unlabeled training data. Like so, in the data set that I described, there were three sources. Amazon, Yelp, and something else. I used Amazon as the training data, and I'm using the other part as my unlabeled data. So again, I'm saying again and again, I mean, it may be confusing, but maybe if you look at the data, you'll understand what I'm talking about. I actually took a labeled data set, but I removed the labels for doing this, for weak supervision. Because the goal of weak supervision is I have a lot of unlabeled data, and I create noisy labeled training data set out of it, and then train some model. So as I described before, the way it works is you use some labeling functions based on some heuristics. You learn some kind of label model based on the output of such labeling functions, and you convert whatever you learned from this label model into training data, which can be used by any machine learning and deep learning approach. So I'll walk you through that process now for this data. So I used very simple labeling functions primarily because this is not my actual problem scenario. I'm just using it to illustrate. So the label functions I used were just looking at positive words and negative words. Like if there is a positive word, or if there are more positive words in my sentence in my text than negative words, I label that thing as positive, otherwise negative. And and I'm not doing anything for the scenario where positive words and negative words are equal, because the goal of these labeling functions are not to be 100% precise and accurate, but to be, it's okay, they can learn from noise. So there may be a single sentence which gets a label positive from positive labeling function, or gets labeled negative from this labeling function called negative. So that that instance at the end of applying all these labeling functions may have two or more labels. And that is exactly the kind of scenario that Snorkel expects. That's how it's supposed to work. A single text may have multiple labels or no label at all. That's why I have this abstain here. If I'm not able to, if I'm looking at something and then I don't find positive words or something like that, then this labeling function just abstains from making a label. These are not the final labels that we use for our training data. This is the labels that we give to the labeling function so that it learns and creates some training data. So, and I also had one more labeling function in the code. You can take a look at that later. But how do you evaluate whether these labeling functions are good? What are we expecting? So here, Snorkel gives some labeling function analysis here. That is, it talks about, so polarity here is what it is doing, like what kind of label it is taking. Coverage is how many training examples does this labeling function operate on at all? Like how many like let us say there are 1,000 examples here, in almost half of them, in 46.95 of them, it's able to make a decision. It's not saying abstain. Overlaps indicate how much of this labeling function, the examples that it considers overlaps with other labeling functions. And conflicts are the examples where one labeling function gives one prediction, but the other one gives a conflicting prediction. So for us, good labeling functions should actually have good coverage with less overlaps and with less conflicts. But then writing good labeling functions also require a lot of domain knowledge. Even for this easy problem like sentiment analysis, the simplest labeling functions that I could think of were positive and negative. So they are not too bad to start with, but then they are not like too good either, as you can see from these numbers here. They're not good enough labeling functions, but I'm still going ahead because I'm just using them as illustrations. In a real world scenario, it actually makes more sense to spend time thinking about what these labeling functions are and how to do them. And it clearly depends on your problem domain as well. And here is where some kind of domain knowledge is useful. So instead of asking your domain experts to hand label the data for you, which can be very expensive in terms of their time, you can probably get some heuristics from them to develop these kind of labeling functions. So in that way, you're still involving the experts in building this kind of data set, noisy data set, but it's not like as intensive and as expensive as making them hand label a large data set for you. So when I say all those things, then one may ask, like, how many labeling functions do we want? Ideally, as much as we can, such that no two labeling functions overlap too much, and together they should achieve maximum coverage of your data. So let us say I have like 5,000 unlabeled text samples, and I want to do this kind of sentiment labeling, positive versus negative. It's not useful if I write two labeling functions which cover like 2,000 examples among them, because I'm still not using the other 3,000 examples, and I need to create a label data set. So ideally, you need to write your labeling functions with such a way that you cover as many of these unlabeled examples as possible. And this is the most challenging part in using weak supervision. We need to know some domain knowledge. We need to either know ourselves, acquire it, or get, like say, interview domain experts or something like that. And this is also what, if you look at Snorkel's use cases, like in the website, you see a lot of use cases of Snorkel used in Google, Apple, clinical companies, and all these things. This is where you see the most work goes into, like how to create these labeling functions. So here I took two very simple labeling functions because I don't have anything at stake here. I'm not deploying anything in production. But in reality, like if you're doing weak supervision, this is where you will spend most of your time. So I use these two, and there's one more labeling function in the code. I use those labeling functions to create a noisy labels for my data, and then I use that to actually create a final noisy training set. And at that point, like you may wonder, what is the like, I mean, why do you want to create that, and how do you create that? Like, let us say I wrote 10 labeling functions, and for a given test set, 5 of them are predicting positive label, 2 of them are abstaining, 3 of them are predicting negative label. How do I make a decision for this data point? So one easy way to do it is to just look at the majority. Like here, 5 functions are created for saying positive, 3 functions are just abstaining, not predicting anything, 2 functions are predicting negative. So let us give positive label to this. So that's one way of creating label training data, just following majority vote on per data point basis. But Snorkel also has a more advanced labeling model to learn some kind of confidence weighted label representations. You can also use that if you want. So here's a code snippet from the notebook related to this point, where I just try both. I use the majority label voter, I use the label model. And what I'm doing in this snippet here is I'm not training anything. I'm just using taking those predictions and seeing how it does on test data. So even without doing anything, just using these label models, I get an accuracy of over 70%. I mean, you have to keep in mind that my labeling functions are not good in the first place. And I wrote only 3 labeling functions. I don't see a lot of difference between this majority vote and the sophisticated snorkel label model. But in real world, you will see the difference if you write good labeling functions. But then at this point, just looking at this, one may wonder, why do I need any other model? Why can't I just use these labeled model predictions? The problem with using this labeled model as it is, instead of going from labeled model to training data, is that it abstains from predicting for a lot of data points. So what if there is a new test sample where all the learning functions just choose abstain? So what do you make the prediction to be for that one? So that's the reason why you learn a label model where it makes a final prediction per label. And the goal is also to generalize beyond that. Like we don't want to use these label functions as our features. We are using these labeling functions only to create the training data, but we want to eventually build a machine learning model which generalizes beyond the training data. So that's the reason why just using this label model that I just described may not be suitable. You still may have to create some training data and go on from there. So how do you go from this labeled model to training data? First of all, you filter unlabeled data points, the points where everything shows abstain. And then you use the rest. And then at that point, it's just, you can use bag of words or sentence transformers or anything. So what happened in this case is that for me, like where is this code example? Yeah, so here I had like 2000 test training examples, but I think using my 2 or 3 labeling functions, only 1200 or 1300 of them got labeled. So I had to discard the remaining 700 labeled training examples, unlabeled ones, and use the rest to train the model. So that is what I did here with bag of words features and with features from a transformer model. I'm showing only the slides. I'm not showing any notebook. I just have a screenshot here. Can you see that? Okay, so with bag of words features, I have actually a very bad model with just 61% accuracy. Oh, can everyone see my screen? Okay, yeah, it seems to, okay, good.
Yes.
Yes, so I'm showing only the slides. I'm not showing any code here. Whatever I'm showing here are screenshots from my notebooks, which are on the GitHub website. Okay, so I used this artificially generated training data from Snorkel to train 2 sentiment classification models, both using logistic regression. But the first one uses just bag of words features, and the second one uses features from sentence transformers. So the first one, it gets a test set accuracy of 61-62%, which is actually pretty bad. But then if you think of this scenario where, if you remember, when I used text blob, I also got 62%. So yeah, it's not, I mean, it's bad, but it's not like the worst possible scenario. With sentence transformers model, I got an accuracy of 73%. If you compare this with Azure had 84%, so this looks bad. But then this is a scenario where I didn't actually have any labeled training data set. I created a labeled data set automatically without any manual labeling. And I used that with my to build a model, which I tested on my manually labeled test data. So if you don't have Azure sentiment analysis, if you don't have text blob or anything, you had a sentiment analysis problem here without any labeled data, and you still managed to get 73%. So that's how you should compare this weak supervision approach with others. because this weak supervision is not like an end in itself. It's the primary usefulness of weak supervision is to build a first model, a good first model, like a decent first model, a strong baseline. And from there, the idea generally is that you don't stop there. You build a model, and once you have some model, you have some means of collecting more and more data, and you proceed from there towards transfer learning or active learning or other things. And then eventually you have large enough data to actually build deep learning models or machine learning models. So when you look at these numbers here, you have to look at that in that context. You are looking at the first solution. You are not looking at your final solution. You are looking at your MVP. So here we managed to get 73% accuracy on this problem without an actual training data set. So that's what you need to look at here. Not 73% in isolation and say, compare with say Azure or something and say, this is like a bad number. This is like your first number. So the pros and cons of weak supervision. It's a quick way to generate label data programmatically, automatically. It's tried and tested. It's used in many industry use cases for NLP and also beyond NLP. It's useful to build a first solution very quickly. But the cons with this is we have to develop label functions, and it won't be easy unless we have a clear domain knowledge or we have domain experts for that. So how does Snorkel compare with Spacey to generate the labels? I haven't used Spacey to do weak supervision, so I can't comment on that. But at any rate, Snorkel itself does not do anything, right? It's more about our own labeling functions. If our labeling functions are bad, then we are not going to get much out of Snorkel. And I'm assuming any weak supervision anywhere, even if Spacey implements it, is going to be the same. It's about our own labeling functions. So with weak supervision, that is the point where we need to put more emphasis on, rather than am I using Snorkel or Spacey or SK weak or anything like that. And also, yeah, and coming back to this pros and cons, this approach may not work well for all kinds of NLP problems. Like say, for example, machine translation. I don't know how to create weak supervision based data set for machine translation. I don't think people do that. I mean, I don't know much about machine translation. It suits well for some kind of problems, like say some relation extraction, name entity recognition, text classification, these kind of problems. But it's like these are also some of the most commonly seen industry scenarios. Like it's, I took an example of machine translation, but I don't think that's the most common scenario where you have to develop a solution from scratch. So this approach is more useful in many common industry scenarios that you see, although it may not cover every single possible NLP scenario. That's what I want to say before ending this part on weak supervision. However, I told about this case study when I started that I actually have my labels. I'm just not using them here. I actually have a label training set in this particular scenario. I just did not use the labels while doing weak supervision, just so that we have a point of comparison. So how do these approaches, like using an off-the-shelf solution like Azure or TextBlob, or using weak supervision, how do they compare to a more optimistic scenario where I actually have some label training data? In this case, we can do two things. We can train our own classifier with whatever training data we have, or we can fine-tune a pre-trained model using our data. The test set, note that I'm using the same test set throughout in all these scenarios, from Azure to this one, I'm using the same test set. So here, why do we need to train our own classifier versus when do we fine-tune a large language model? So the advantage with fine-tuning part with transfer learning is just that even if we have a smaller training data set, we can still benefit from a larger pre-trained model. And of course, training our own classifier, it has its own advantages. We can do whatever we want with it. Basically, we can customize it in any way we want. We can add some rules if we want. We can make it like a hybrid rules plus machine learning thing, or we can combine multiple models and make a prediction. We can do whatever we want if we just train our own classifier. Everything is under our control. And transfer learning is also more useful in a scenario where you already have a large language model or a large NLP model, and you have a smaller data set, and you want to somehow use the knowledge from that model to your task. So I'll talk about both these scenarios now, and at the end, I'll just compare how everything is doing. So training our own classifier, I'm just taking the table data set. I'm just using this. I'm just doing very simple bag of words prediction. And it's also like I'm not also doing anything. Like I'm just taking the 1,000 most frequent words and using vectorizer, count vectorizer to transform my training and test data, and just using simple logistic regression. And my goal here is not to show all possible different ways of representing features and learning models, but I'm just illustrating one possible way of doing this. That's why I chose the simplest possible procedure. So this procedure gave me 74%. Like I had my label data set, I'm using this bag of words, and it gave me 74%. But with Snorkel, when we actually don't have any label data, I already got like 73% or something, right? So in this case, this data set may not be like, it may not be a very good idea to train my own classifier with bag of words. With SBERT, with sentence transformer features, I used this model called Paraphrase TinyBird, which is the smallest model, pre-trained model, I think. And there are several hundreds of like 100 models or something on that website. You can try them. Again, I took the labeled test set, labeled training set. I got my feature representation from SBERT. I again used logistic regression. And I got an accuracy of 88% here. Now here, you see some difference, right? Like when I'm using Azure, I got 84%, but then I didn't know what to do with 10% of my predictions. When I did weak supervision, I got like say 73% or something, which is not bad, but clearly when I have a lot of label, when I have like not a lot, 2000 labeled examples, I managed to build a classifier. Classifier is very simple logistic regression classifier, but my feature representation is based on transformers. Then I got 88%, which is like a good number. It's like a good number, good sentiment classifier. It may not be perfect. You still have to do a lot of error analysis to understand where it is doing well and where it is failing. But 88% is a good number for like that kind of binary classification problem. So that tells us that it's good if we have our label training data. If we don't have anything, we are starting with this unlabeled scenario. We may not be too bad. We are starting in the 70s, 73% or something like that. And we can go from there. From here, the second labeled training set scenario I talked about was transfer learning. When I used this SBERT features earlier, that is also a pre-trained model. I'm also relying on a pre-trained model, but I don't do any fine tuning there. Like, what is the, so that is more like a zero shot scenario. I'm just taking that pre-trained model and using it to do my classification. The difference when I talk about transfer learning is that I'm not doing that. I start there, but I somehow like I retrain the pre-trained model to suit my task. So I keep what all that model has learned, that large model already knows about language, but I change it a little bit so that it suits my classification task. So that's the difference between just using, say, some kind of BERT or sentence BERT or something like that, just like as a feature extractor, rather than fine-tuning it and using it like a transfer learning scenario. So it may sound complex, like when I describe it like this, like the model's weights are altered and all these things. But actually, we have a lot of easy to use transfer learning implementations now, like with Hugging Face. So it's not that difficult as it sounds in terms of implementation. So I just took this code snippet from Hugging Face tutorial on using transformers. And it's just that this simple. You just choose the training arguments and then you choose a model as a base. Like here, I chose DistilBERT because it's a smaller version of, less bulkier version of BERT, which is quite good for many tasks. And then I gave it my training arguments. I said, this is my training data set and this is my evaluation data set. And then I'm just computing the metrics. This actually gave me 92% accuracy on the test set. And so what I did here was I took this DistilBERT model as my base. I fine-tuned that model for my sentiment classification task, because I had some labeled data set in this scenario. And I used that fine-tuned model with the same test set I've been using all the way. So this 92% accuracy is on the same test set that I was using on Azure, I was using with text blob, I was using with weak supervision, and so on. So this is like, we talked about two scenarios, training our own model from scratch versus doing transfer learning. Pros and cons of this process is that we have more control over the training process. We may get better performance as this is custom made for our data. As we saw, like both these models did better than Azure and weak supervision and other things. However, the problem is with these models is that we need large training data sets as a starting point. And we need more knowledge and expertise on how to experiment, what to discard. Like here, I just showed with logistic regression. It may be possible that if I use more complex classification approaches, I may get better performance. So we need to know those things. So those are like more like problems with this approach. The simplest case where we don't have to know anything is if the ready-made problem is available as a solution in like one of these cloud providers. You just follow what predictions they give and you're done. But that's also the most unlikely scenario in a practical industry situation, right? So that's why I've been talking about all these different ways of doing this. So here's a quick summary of all approaches. The first part is when we don't have any labeled data set in labeled training data. Predictions from Azure gave me an accuracy of 84%. Text blob gave me an accuracy of 69%. Snorkel gave me an accuracy of 73%. We talked about the pros and cons of each of these kinds of approaches. When we do have some amount of labeled training data with the same test set, training my own model with bag of words features gave me 74%, but using more sophisticated feature extraction as it is without doing any fine tuning gave me 88%. Transfer learning, I got 92.7%. So there's a question here related to this before I proceed. Can you please explain why you selected solely the Amazon dataset as test and not used it in training as well? The reason is Yelp and IMDb are different kinds of data. Like Yelp has more like hotel reviews and IMDb is movie reviews. Amazon had more like product reviews, different kind of product reviews. So I wanted to see whether a model learned on another kind of like movie reviews and hotel reviews will also do well on more general Amazon reviews kind of data set. So that's the reason why I just split them like that, because it's an easy split for me to make. Like just take two of them as training and one of them as testing. Other than that, I don't have any other reason. If you want, you can also take 1/3 of each as training and 1/3 of each as testing and 2/3 of each as training. So this was my motivation to choose like that, to just see like how, because by default, if I do this, by default, my test data will be out of date. So I can check whether my model is more robust. Otherwise, if you don't do that, and if you want to check the robustness of the model, then you need to also analyze your predictions in terms of like how is it doing on IMDb, how is it doing on Yelp, how is it doing on Amazon, whether it is doing better on one category versus another, and so on. So yeah, I mean that's my only reason. There's no complex logic behind that. I don't work for Amazon. I work for government. Okay, so that's a summary of what I tried. And here are some caveats on the approach I took. I only wanted to show a range of methods to apply when you encounter this no label data scenario. So I took a relatively easy example, and this is by no means a statement that Azure works or does not work, transfer learning works or anything. In a real world scenario, you need to explore multiple approaches before taking a final decision. With careful heuristics, even weak supervision may give you much better performance than what you saw in this example. So before I stop for today and open up for questions, here's a summary of what we discussed so far. We talked about different means of collecting data, how to do manual labeling, and the need for doing manual labeling to compile a high quality test set. We looked at one possible approach to take using off-the-shelf solution and evaluating them. We looked at how can we develop a weak supervision based approach to build a label data set automatically and then train a machine learning model with that. And we looked at how this compares with the case where we actually have some label data set, like we tried some classification, some transfer learning. And there was a very brief overview of other methods like semi-supervised learning, active learning, how do you use them? So there are a lot of things I don't talk about, of course. I don't talk about how to do better feature engineering or different kinds of models, evaluation, how do you compare between them, how do you test them, and so on and so on. But there's only so much you can cover in like 1.5 to 2 hours, right? And I also wanted to focus on this very particular scenario where you don't have any data to start with, and what are the different options you can do to build a first model. So I'm just revisiting these 2 slides that I had earlier before I started this coding part. So just to recap, so let us say we have no data to start with. What do we do? So the first and foremost thing I personally endorse a lot is to understand your requirements, create a high quality, maybe small but manually inspected labeled data set to use as your test data. Evaluate off-the-shelf solutions if they exist. Look at weak supervision and evaluate its performance with your high quality test data. Once you have some kind of baseline weak supervision model, evaluate whether you can do transfer learning, whether you can do semi-supervised learning, active learning. So as you reach this point of as you reach this stage of your project, it's relatively more mature than where you started. You have some amount of label data. And then you can explore more sophisticated machine learning models. So the point I'm trying to make again and again is there is no one stopping solution. It's like you keep updating your model over time. So what I'm trying to show here is some of the first solutions you can build. So this is where I'm going to stop. I hope this tutorial gave you some overview of what to do when you encounter a new NLP task without a labeled data. Here are like a couple of references on some like how to approach NLP in low resource scenarios. And yeah, this is where I'll end. And yeah, we are open to questions now. Okay, so we have one question with which we'll start. Any thoughts on recommended tools or approach for creating labeled dataset from noisy chat transcripts of custom NER? So I would suggest for this question, I would actually, so there is a shared task organized by Amazon right now. It's called multi-co NER. I think it's very similar to this problem scenario where you described. They have a lot of these chat transcripts, and they have an NLP problem where they created a labeled data set, but it's not clear to me. I don't know yet how it is created, but maybe it's good to look at that website where they describe how they created this data set, and that may give you more idea of how to approach this particular problem. I mean, like I said, it's a new shared task, so I didn't study the whole website in detail, but there they describe this exact scenario that you talk about. Okay, so, and next one is, so how would you approach domain-specific tasks, NLP tasks like medical or legal documents, which are largely unstructured? And okay, so this is what I did before. So I encountered this scenario of legal NER before, and we did the same thing that I showed here. Like we first created a small NLP, a small label data set using Prodigy, the tool called Prodigy, which has a similar interface like Docano, but it's more like it's a licensed tool, and it has more functions to adopt an existing NER model as you create a new label training data set for legal domain. So that's what we did. And we also tried semi-supervised learning. Like once we had a small amount of labeled test set, which is manually labeled, we kept redoing an NER model and using the high quality predictions as additional training data. And we did it in multiple loops like this to finally create a model that is doing better with legal texts. So that's what we did. And I would say that is still the way to go as far as I know. I hope that answers your question, and that's not an easy thing to I mean, that's not an easy process, but I think that's the only process that is guaranteed to at least work to some extent. Okay, any other questions? We still have like 15 minutes before the session ends. Okay, so no, I don't think this part is covered in the book. At that point, it's briefly mentioned in chapter 2 of our book, but we don't explicitly cover examples of weak supervision or semi-supervised learning or anything. Yeah. It's something that occurred to us after we gave the book for final, give the final version of the book. So the book has a website, practicalnlp.ai, where you can find information about where to buy the book on Amazon, and you can also search for practical natural language processing online, and you'll find the book. Okay, there's a so I shared the slides already, and I think the talk is being recorded, so it will be available at some point of time. Any other? Okay, so is there a good real-world application based on weak supervision? I can't point to one application, but I know for sure that Amazon, Google, my colleagues who work in Alexa team and all this in Google, they all do a lot of weak supervision. So we may not directly see a product that markets saying that I'm using weak supervision for this, but they publish a lot of papers showing weak supervision's use in conversational AI in doing this intent classification and things like that. So yeah, I mean, I can say there are a lot of NLP applications out there which are using weak supervision at some point during the project life cycle, maybe like when the product is less mature. Yeah, here are the slides again. If here are the slides again, if anyone wants to take a look. Okay, so did I miss anything here, or did I cover all the questions? I think I covered all the questions that were asked in the chat window so far. And yeah, I'm attending TMLS, so I'll be available online during this time. I mean, as much as possible. And the slides also have my email if you want to contact me. So yeah, I mean, if there are no other questions, then maybe we can, I don't know, we can leave like a few minutes early.
Thank you so much, Sowmya. I really appreciate it. This is very helpful. I hope everybody else has found this very helpful as well. And thank you for making yourself available, for taking the time to prepare for this, and willing to give back to the community in this way. I really appreciate it.
Yeah, thank you for the opportunity too. I enjoyed doing this.
Yeah, so you can find Sowmya, as she mentioned. Her book, her email is in the slides, and as well, she'll be around towards these next couple of days on the Hopin platform. As well, I just wanted to remind everybody we have the app, the Whova app. So you would have gotten a notice to download that when you registered for your ticket. So you could go back and check that. In some cases, it's going to people's spam. So just make sure that that hasn't got flagged as spam. And then also as well, Wednesday and Thursday, you'll get a specific unique link to join Hopin. So Wednesday and Thursday will be on the conference platform, hopin.com. You'll have a link being sent very shortly, so you can join that. But anyways, thank you so much, Sowmya. I really appreciate it. Thank you everyone for joining, and we'll speak with everybody soon, and hope to join you again for the following sessions today and tomorrow for the workshops. Thank you.
Yeah, thank you everyone. Have a good conference.